So in the nucleophilic substitution reaction, this is the of haloalkanes. These are sp3 carbons, remember, so you may think something else is a substitution at an sp2 carbon, but here we're only talking about sp3 carbons. And for this kind of reaction, you should assume only sp3 reactions will work. So in this particular kind of case, we're doing a substitution at the sp3 carbon. Let's have some little bit of nomenclature here. Leaving group is the halogen that's going to leave from the carbon. And so halogens that leave from the carbon are fairly common. The most common ones are chlorine, bromine, and iodine. Fluorine has a really strong bond between carbon and fluorine. And that's partly because the orbitals are about approximately the same size. So there's good orbital overlap, and it's a strong carbon-halogen bond. The other halogens, the chlorine, bromine, and iodine, are much larger than the carbon, and they don't make strong bonds. Actually, the bigger the halogen, the weaker the bond, and this is why this reaction can work, because not only are we replacing a weak bond with carbon to a stronger bond with carbon, but also the halogen that comes off is a halide, which is fairly stable. Recall that halide anions are the conjugate bases of strong acids. They're weak bases. They're relatively they're stable on their own. And so here's some examples of nucleophiles that we showed on the last page. Actually, I didn't mention nucleophiles, so let me finish that up. Nucleophiles are typically negatively charged, although they're not always negatively charged. They're Lewis bases, so they have electrons to donate. They donate the electrons to the tetrahedral carbon, and so that we don't violate the octet rule, the halogen has to come off. So here's some examples of nucleophiles in a substitution reaction. So the substitution reaction is on top with a nucleophile coming in to a methyl halide or a halomethane. And the nucleophile substitutes for the halogen, so it makes a carbon nucleophile bond, and we also make a halide anion as the product of that. And so the nucleophiles that can do this reaction, some of them are on the column on the far left of the table. So hydroxide, alkoxide, that is an alkyl group with an oxygen, and that's an anion. It's an alkoxide. The sulfur anions are also very good nucleophiles. Halides are pretty good nucleophiles, even though they don't make strong bonds. They react fairly easily with other alkyl halides. Nitrogens are compounds that have lone pairs that can participate in substitution. So these are nucleophiles. They have to donate their pairs of electrons. Nitrogen, oxygen, sulfur can do this. Halides can do this. Carbon anions can do this as well. Because carbon anions have a lone pair of electrons to donate, and so we'll see some examples of this later. The reason I'm bringing that up is because we need to think about nucleophiles as we go to the right in the periodic table in the second row: carbon, nitrogen, oxygen, fluorine, and we need to think about the ones from the column, the halogen column, and also the oxygen column. And as well we'll sometimes see the nitrogen column. There's phosphorus below nitrogen. So in any case, when those nucleophiles react with, for example, chloromethane, the products that you get from those substitutions are the ones in the second column. So in each case, we have in each of the cases where there's a negative nucleophile, that is negatively charged nucleophile, we get a neutral product. And the cases where we have a neutral reactant, recall that the nucleophilic atom, nitrogen in the case of ammonia, or oxygen in the case of water, that's now going to have lost a pair of electrons when that lone pair binds to the carbon, and so it's going to be positively charged. If we calculate the formal charge, it will be positively charged. And so, we're going to have to keep that in mind, what the charges are after we make and break bonds, which is something I've mentioned before. Every time we make and break bonds, we should be considering formal charge. So there are two limiting cases for nucleophilic substitution. By that we mean that there are two possible mechanistic extremes, that is, two mechanisms which can give substitutions. And there's a big difference between the two of them, and the big difference is what the timing of the bond breaking and bond making is. By the way, that's not the only big difference. We'll see other big differences a little bit later on, but for for now, that's what we're going to consider. What is the timing of the bond making and bond breaking for the two extreme cases? And the first one that we're going to look at is an SN2 substitution. So this is a substitution at a tetrahedral carbon with a leaving group such as a halide. We'll see other leaving groups in other chapters, but halides are the subject of this chapter. And so the SN2, this S is for substitution, N is for nucleophilic, 2 is for bimolecular because the two components, the nucleophile and the electrophile, are going to be in the transition state. They're going to participate in the transition state of the rate limiting step. And therefore the rate of the reaction is going to follow the kinetic expression shown at the bottom of this page. The rate of reaction is some rate constant, that's small k, times the concentration of the haloalkane times the concentration of the nucleophile. So here's a reaction in the scheme below of a substitution using hydroxide as the Lewis base or the nucleophile and using bromomethane as the electrophile. Let's look at this in great detail. And so including the transition state we're going to look at in detail. And so the nucleophile, and I put attacks in quotes, I changed that. That's really old terminology having to do with when these ideas were first gelling way back when in the latter part of the 19th century. And folks were pretty militaristic then. So they looked at the donation of a pair of electrons from the hydroxide to the carbon as an attack. The hydroxide is attacking the carbon, the bromomethane carbon, for example. Gosh, if this was in the 60s, maybe we'd be saying they're going to have a conjugal interaction. But in any case, there is a bonding interaction between the hydroxide and the carbon, and we're kicking out the bromide. Maybe another way to think about that is the hydroxide is marrying the carbon, and the bromine is divorcing the carbon, and going off with all the wealth of electrons. Bad joke, sorry. But in any case, in the transition state, we're making and breaking the bonds that are being made in this reaction process. So we're making the carbon oxygen bond from the hydroxy. We're making that in the transition state. It doesn't exist before, but it exists completely after. And we're breaking the carbon bromine bond, which had a full bond before and no bond afterwards. And so in the transition state, we're halfway through these processes. We're making and breaking those bonds. Notice the D minus, the hydroxide had a full negative charge at the beginning of the reaction, and in the middle of the reaction it has a partial negative charge, and at the end of the reaction it has no charge. And so that's changing in the course of the reaction, and the transition state summarizes that change. And the carbon-bromine bond is fully made, and the bromine has no charge, and in the transition state it's partially charged, because in the products bromine is fully charged. So you could think about this as everything is halfway in between. So let's go through a little bit of nomenclature to remind ourselves. The nucleophile is the Lewis base. It's the donator of electrons. The electrophile is the acceptor of the electrophile of the electrons. You can call that electrophile carbon. You can call it the electrophilic carbon, but the whole thing is called the electrophile. In the transition state, we have those partial bonds being made and formed. We're going to talk about the geometry of that in just a moment, but we have partial charges in the transition state, reflecting the changes in charges between the atoms. If we're drawing the transition state, we should put in the double dagger, as I've done in red on the top right-hand side of the bracket. That is the transition state. So in the product it says, note inversion of reactive center. And I think that's a little bit hard to see here, so I've added a couple of things. Let's look at the bond, at the orbitals that form the bond in the starting material. So it's a carbon-bromine bond. The carbon is an sp3 orbital that's bonding to the bromine orbital to make that sigma bond. So what's happening there is the nucleophile is coming in and beginning to bond to the bottom, to the opposite, the lobe opposite of that's bonding to the lobe of the carbon opposite to the one that's bonding to the bromine. So it's reacting with that small sp3 lobe and beginning to form a new bond. It's halfway formed that new bond in the transition state. And in the product, we have a small lobe that used to be the lobe that used to be a big one that bonded to the bromine. It's now small because the bromine completely left. And essentially what we've done is we've inverted that lobe so that lobe can make a bond to the hydroxide coming in. And when all that process is happening, the hydrogens are migrating from the side opposite that the bromine was on, that is to the white side of the lobe. That's a different phase. That's what that means. The small lobe is white, and that's a different phase than the larger lobe, sp3 lobe. Those are migrating from the left side there, opposite the lobe that bonded to the bromine. Those are migrating oppositely to the right, so that we get a new tetrahedral product. We started with tetrahedral, we end with tetrahedral. And so those are flipping over like an umbrella flips over in the wind, is how you ought to think about that, which is what I was told when I was an undergraduate, in fact. The energy diagram for that process is shown in the next slide. And so the transition state is shown. Actually, they got the delta minuses correct in this case rather than the D's. Notice the activation energy. There's only one hump here. This is a concerted reaction, and so everything is happening at once. We're making and breaking bonds. This is an exothermic reaction, and you should think about this way. The carbon-bromine bond is not so strong, whereas the carbon-oxygen bond is strong. And that means that the carbon-bromine bond is going to be higher in energy than the carbon-oxygen bond. So everything else is the same, other than we've changed from a carbon-bromine bond to a carbon-hydroxy bond. Well, not everything is exactly the same. We have, instead of a hydroxide, we've got a bromide, which is also energetically good. Remember, bromides are very weak bases because the conjugate acid is so strong, which means that bromide is stable, and it's going to be much more stable than hydroxide. But because of the weaker carbon-bromine bond, and because of the weaker basicity, that is the greater stability of the bromine anion, this is an exothermic reaction. And so you should say for SN2 reactions, they're generally exothermic. And you could draw this every single time as far as I'm concerned. But this is what you would draw if I asked you for the transition states. You should put in potential energy or just energy on the y-axis and reaction coordinate on the x-axis. So the other limiting reaction, and I think this is the last slide for this section, is the reaction in which the halogen is lost first before the new bond between the carbon and the nucleophile occurs. This is called SN1 because the rate of reaction will only be dependent on one component, that is, it's unimolecular. It's only dependent on the concentration of the haloalkane. And so we'll discuss that in the next slide presentation. But between now and then, think about why we don't consider the case where the nucleophile adds first and then the electrophile leaves, because we've essentially looked at the other two extremes where the nucleophile and electrophile are both forming and breaking bonds at the same time. We've considered the case where the halogen leaves first. We haven't considered the case where the nucleophile comes in first. Give that some thought.